Okay, chat box is active. If you have a question or you have a specific area that you're uncertain about, interrupt me. When we get done with it, I'm going to ask you for some feedback on the exam as well. So let's start this off. Of course, I mentioned to you it's really important that you understand variable types, because as we move through the rest of the semester, you're going to be learning different kinds of statistical tests, and the different types of tests are specific to certain kinds of variables. Bar charts, frequency charts, frequency tables, and so on and so forth, specific to categorical variables, nominal variables, binomial variables, which is just another kind of categorical variable, and things like mean, median, mode, box plots, histograms, and so on and so forth. Those are specific to numerical variables. We're also going to learn about other kinds of tests. The t-test, comparing means. We're going to learn about chi-square, which involves categorical variables. We're going to learn about analysis of variance, which, going back again, is comparing means, which are numerical variables. Then we're going to learn about correlation and regression, where we look for an association between two numerical variables. You get the picture here? All of these tests are specifically geared to evaluating relationships between certain kinds of variables. So that's why I kind of beat this to death a bit. Okay, so let's take a look at question number 1. In a date set, we work with a number of variables associated with a sample of birth records in North Carolina, and these are actually the variable names as we were going through them and the descriptions. Okay, then let's see which ones that these actually are. Okay, so gender. What would you guys say that gender is? Right? Nominal. Right? Nominal or categorical. How about the age of the mother? Mother's age. Numerical, right? Okay, I'm going to go through them quickly so that if you have a number of weeks of gestation. Weeks is kind of like a little bit ambiguous. So you go back up here, and that's the reason why in SPSS we have the variable name, but then we can also apply a label to that, something that's more descriptive, like weeks of gestation. So that could be, so 9 times 4 is 36. So it could be 36 weeks, 38 weeks, 24 weeks, and so on and so forth. That's the number of weeks of gestation. That, again, is a numerical variable. Okay. How about marital status? Well, that could be nominal, right? That could be nominal. So it could be married, unmarried. That could be a binomial or a dichotomous nominal variable, just married or unmarried, or it could have more values. It could be married, divorced, separated, previously married, widowed, and so on and so forth. So still nominal, but it could in some cases be dichotomous, just 2 values, which we handle a special way sometimes, or it could be have more values than that. So that's going to be nominal also, or categorical. Ethnicity. Well, ethnicity is basically a name. You know, white, black, Hispanic, so on and so forth. So that's nominal also. Okay, the pain scale, mother's reported pain level on a scale of 1 to 10. Well, it kind of looks like a number, right? 1 to 10, but that number is really subjective. You know, it could have just as easily been a little bit of pain, more pain, a lot of pain, really intense pain, right? Those numbers are really names in a sense. So that pain scale is a special kind of nominal variable that we call, anybody remember what we call it? See if I get that online too. You guys hear that behind me? It's right, ordinal. Good. Excellent. And the T grams is the birth weight infant grams. It's in grams, so it's a numerical variable. There's also a associated one that's T ounces, which is the birth weight of the baby in ounces, also a numerical variable. Okay, so when we have a histogram, that histogram or that box plot, histogram or a bar chart, frequently the way that they're laid out, the height of the bar represents a frequency, either a frequency or a percentage of the population that's represented within that bar. Okay, so in the case of histograms, they're all connected because literally, if you're not in one, you move over into the other, right? So there's actually this is actually a kind of a specialized bar chart 4 numerical variables. So if it's 4.9 days, maybe it's in one, and at 4.5 days it's in another, and so on and so forth, if we were going to define it that precisely. The height of the bar, of course, is the frequency or the percentage of the people or subjects in that particular bar. So the most frequent number of days stay in this rehab center or hospital is 12 days. 5 people stayed for 12 days. The lowest is either 6 days or 14 days. Only one person stayed for exactly 6 days and one for 14 days. So the x-axis is the length of stay in days. The y-axis is the frequency, the number of people that are represented in that number of days stay. Okay, so let's look at this and see what we can tease out of this information. How many patients stayed in the center for 10 days or more? Okay, well, just simply that's the number of people that are represented in these bars. And you can look at this a couple of ways. Okay, we got 4 that are 10 days. We have 2, then we're up to 6 that are 11, and we have 5. So we have 18. Did I say, what was it, 6? Oh, what 5, 11. Am I up to 11? 2, 4, 2 is 6, and 5 is 11. 13, 14. So I have 14 people that stayed for 10 or more days. Right? I didn't make a mistake there, did I? Good. Okay. So you have 14 people. So I'm going to put in a 14 there. Okay. So now, this is kind of a simplistic thing. You could also look at the area of these boxes representing the percentage of people that are in that range, greater than 10 days. So the area of these boxes. That kind of introduces you to the idea that if we have a large number of boxes and a very large population, that these boxes can get skinnier and skinnier and represent more and more people, and they actually can be described as a curve, like a distribution. And that distribution can be represented by areas of that distribution, representing the number of people that are stayed for more than 10 days, or the percentage of people that stayed for more than 10 days, which is represented by the area or the percentage of the area that represents. Okay, so that'll come in later on. So what's the probability of staying in the center for fewer than 3 days? For fewer than 8 days, excuse me, not including 8 days. I shoved that in there. I shouldn't have needed to, but not including 8 days would be 4, 5, 8, and 2 is going to be 10 people. Okay, now what's the probability of staying in the center? Given that a patient has stayed in the center for 11 days or more, what's the probability that the patient stayed for 14 days, given given number between 0 and 1? In other words, what I'm asking there is for a proportion, like not a percentage, but a proportion. So what's the proportion of the probability that they would have stayed there that long, given that we know that they stayed for at least 11 days or more? Well, this is our first look at conditional probability. Given the condition that has occurred, that these people have stayed for 11 or more days, we're only going to examine people that satisfy that first condition. So what's the probability of that, given that they've stayed 11 days, and that would be 2, 7, 9, 10 people. Given that there are 10 people, what's the probability that they stayed for 14 days? Well, only one person out of 10 that satisfied that initial condition stayed for 14 days. So that's going to be 10%. But since I asked you to provide it as a proportion or a probability, it's going to be 0.1 or just 0.1 if you want that. Oops, yep, I'm sorry there. Okay, yep. What was that one? That was 10, right? No. Did I ask for a proportion there? 0.33? Okay. 0.33, and this is 0.1. Okay, good. All right, so that's what we did with that. So, okay, let's move on to diagnostic testing. So as far as diagnostic testing is concerned, we learned that the specificity of a diagnostic test represents how good it is at diagnosing people, identifying people that have the disease. So if we say that a diagnostic test has a sensitivity of 90%, that means that if you have the disease, the probability is 90% that it will correctly identify you and say that you're positive for that disease. You have a positive test. Okay, if we had 100 people, it would correctly identify 90 out of those 100. Okay, since the sensitivity is only 90%, it's going to be wrong 10% at a time. So let's take a look at this. Consider results of evaluation of diagnostic tests on a random sample from a population. What's the prevalence of the disease in this population? Well, how many people did we actually examine? What's the total number of people in this population that we sampled? 1,000, right? So you have 1,000 people. How many of those people are positive, right? Actually have the disease? Okay, anybody want to give me some help with that online? Right, exactly, 100. 100 out of 1,000. So the prevalence here is 90%. 10%. 10% of the people in this population have this disease. So I'm going to put that in as 10%, 0.1. Okay, what's the sensitivity of this test? Well, 100 people have the disease. It correctly identified 90 of them. Right? Unfortunately, I kind of gave that away ahead of time, because that's kind of what I described already. So the sensitivity of this test, would be 90% or 0.9. Okay, that's sensitivity of the test. Now, what's the positive predictive value of this test? Okay, and the positive predictive value refers to the probability that you actually have the disease if you test positive. Well, I skipped over a couple little things here, didn't I? One of the things I skipped over that I didn't ask you in the test is what is the specificity of this diagnostic test. Okay, now specificity tells you how good this test is identifying people that don't have the disease. So if you don't have the disease, you want to test negative. So you want to know what percentage of people are going to be true negatives, are going to test negative and really be negative. So we have 900 people that do not have the disease in the sample. What percentage of the time were we correct? Well, 702 people out of those 900 tested negative. So we correctly identified 702 out of 900 people. So what percentage does that represent in terms of the specificity of this test? Somebody give me some feedback online. What would that be? Specificity 720 over 900? Is that right? 78%? Okay, probably. I got a probably on this end. Let me check. I'm going to check your work, Melissa. Hang on a second. Okay, let's see. 702 divided by 900 equals 78%. Absolutely right. Good. Okay, so that's 78%. So that means that 12% of the time, it tested these 900 people and found that and predicted that they were positive. So we have 198 people. In other words, 12% of 900, 22%, 22% of the time, these 900, it incorrectly identified them as having the disease or being positive. So these are false positives up here. So 900 people who don't have the disease tested positive. So if we look now at the total number of people that tested positive out of this population of 1,000, turns out that 90 plus 198 or 288 people tested positive. Of those 288 people, only 90 have the disease. So the positive predictive value is the percentage of people that have the disease over the percentage of people that tested positive. In other words, true positives over true positives plus false positives, this being false positives. So what is that going to be? That's going to be equal to, it's going to be equal to 90 over 288. So let's get our calculator up. 90 divided by 288. So our positive predictive value here is only about 31%, or about 0.31. Okay, you guys agree with me on that? Now I'm going to ask you to do something else on your own right now. What is the negative predictive value? In other words, of all the people that tested negative, what percentage of the time did we get a correct result for those people being negative? In other words, you test negative, what's the probability that you would really not have the disease? Okay, so I'll give you a second to do that. Yeah, well, it's even more, I think, right? 702. You know, I'm saying this out loud as they're listening to me. I keep forgetting that even though you people are not in the room, that you can actually hear me. Come on, give me a volunteer there to figure this out and let me know what it is. No bold predictors out there? Nobody with a calculator on their phone or something like that who wants to volunteer? I should start giving out class participation points for this or something like that. I really want to keep you involved. That's why I'm torturing you like this. But I'll go ahead and solve this for you. We have 712 people that tested negative. 10 of them had the disease, so they're false negatives. 702 of them didn't have, thank you very much, Melissa. 702 of them didn't have the disease, so they're true negatives. So where negative predictive value is going to be 702, the number of people that don't have the disease, the true negatives, divided by the true negatives plus the false negatives, which adds up to 712. So 702 over 712, which comes out to 98%. Okay, let me just, 702. I'll check your answer there since you put a question mark on it. Divided by 712. Sounds right to me, though. It's going to be 90, but we're actually almost 96%. No, almost 99%. Sorry. Okay. So, I need to blow this up. I hate looking at this. Let me brighten the screen up a little bit so I can see it a little bit better. Okay. No, didn't help much. Okay. So now let's move on to the next problem. Now, consider this before we move on to the next problem. The negative predictive value and the positive predictive value, those are both examples of conditional probabilities. In other words, the positive predictive value, basically, that's the probability that you have the disease given that you've tested positive. And the negative predictive value is the probability that you don't have the disease given that you've tested negative. In other words, we'll only consider the people that had that particular test in considering what the probability is. Okay, that is a conditional probability. Okay, so consider a diagnostic test for cancer that is 99% accurate. That's a really high specificity on individuals with cancer. If an individual has cancer, the test is 99% likely to produce a positive test, basically our definition of sensitivity. It is 90% accurate for individuals without cancer. In other words, correctly identifying people that present and take the screening test as not having cancer. The specificity, how good it is at predicting that you don't have it when you don't have it. Okay, so this test is applied to a population where the prevalence is 0.01, it's 1%. Okay, it's a relatively low prevalence in a population. Okay, actually not that low, but low enough. Okay, if an individual receives a positive test, what is the probability that the tested patient has cancer? Note, probability is a decimal number between 0 and 1, not a percent. Okay, that's what we want this answer. So let's go ahead and answer this question. What is the probability that a tested patient has cancer in this situation? Okay, now there's a few ways that we could solve this, right? One way we could solve this is we could apply a formula that we know. I don't have it handy, so I'm gonna look it up. Okay. Let's see, positive predictive value, formula. See if I can't find it quickly. Okay. Maybe I need to expand that to include conditional probability. Here it is. There's a version of it right there. And I'm going to take that out here. Okay. Get that out of the way now. Okay, let's see what we have here. Basically, all of this is Bayes' theorem here, basically. Remember that we're applying here. Basically, this is telling us that the probability that you have the disease, given that you've tested positive, is equal to the sensitivity times the prevalence over the sensitivity times the prevalence plus 1 minus the specificity times 1 minus the prevalence. Well, let's think about this for a second. The sensitivity times the prevalence, right? Well, the sensitivity is the probability that you get the test right, that you really are positive, and the prevalence is the percentage of people in the population that have the disease. So if I multiply the sensitivity times the prevalence, basically I'm getting the percentage of people in the population that tested positive, that are true positives, that have the disease and tested positive, right? If this were 80% and the prevalence is 1%, we're going to figure out what that is. So this is the percentage of people in the population that test positive and have the disease, true positives. So on the bottom here, I have true positives. And if I recall what we talked about before, the positive predictive value is equal to the true positives over the true positives plus the false positives. So down here, sensitivity times prevalence comes up again. That is a true positive. So I have true positives over true positives here, plus then this must be something that represents the percentage of people that don't have the disease that test positive, the false positives. So how do we get to that? It's 1 minus the specificity. That's the percentage of people that don't have the disease. If 1% of the people have the disease, 99% of the people don't have the disease. So that's what that represents. Times one the prevalence. That prevalence is that, right? Is 99%. Now, the specificity is the probability that it correctly identifies people that don't have the disease. And 1 minus the specificity is the percentage of time that it gets it wrong. So the percentage of time that it gets it wrong times the percentage of people that don't have the disease gives you the percentage of people that are false negatives. So we have false positives, rather. So we have true positives over true positives plus false positives, but in the form of percentages, but it still gives us the right ratio so that we wind up with the positive predictive value, the probability that you have the disease given that you've tested positive. So let's actually run through this. Let's run through this equation for the example that we have here. Okay, I'll see if I can't do it. Actually, I'm going to open up Excel and do it with Excel. Save me a little bit of time. Okay, let's blow up these cells a bit so we can see it a little bit better. And let me reduce the size of this page. Okay, so first I'm going to resolve the top part of this, right? So maybe I can do something. I don't want to get it too small there. We'll read it. Actually, let me move it down below. Okay, I'm going to ask you to help me with these numbers again now. Okay, so the sensitivity in this particular case was, what was it? Anybody remember? 99%, right? So the sensitivity was 0.99. Okay, and the specificity was 90%, was 0.90. And the prevalence was 1%, 0.01. Okay, so that's my starting point. That's everything I need at this stage. So let's resolve the top part of this equation. So the sensitivity times the prevalence gives us the percentage of people in this population that are true positives. Those are the number of people that actually have the disease that tested positive, the percentage of them. I'm going to repeat that down here. Sensitivity times the prevalence is going to be a little under 1%, right? That's the proportion of people that test positive to have the disease. Well, how about the percentage of people that test positive but don't have the disease? Well, that's going to be our false positives. That's going to be equal to 1 minus our specificity, right? That's going to be 10% now, right? Times 1 minus our prevalence. I'm going to put that in parentheses also. 1 minus our prevalence, which is, oops, that got a little disagreeable there because I lifted the cursor there. 1 minus our prevalence, which is now prevalence is 99% of the people who don't have the disease. Okay, let me multiply this out, and that's the percentage of people that are false positives. Let me make sure I got that right. 1 minus the specificity, which is 0.9, which is C3, and times 1 minus the prevalence, which is C4. Okay, good. I think I got it right. So the sum of these two is the bottom of my equation. So I'm going to work this out. So the probability that you have the disease, given that, I'm going to use this symbol called a pipe, given that you've tested positive, is going to be equal to the total positives divided by the total positives plus true positives plus false positives. Okay, which is going to be our positive predictive value is about 9%. In other words, 9%, if you get a positive test given this within this population, the probability that you actually have the disease, even though you got a positive test, is only 9%. So, can somebody tell me why we have, given that the test is 99% accurate at identifying people with the disease, and then it's 90% accurate at identifying people who don't have the disease, why would we wind up with such a poor predictive value? Can somebody tell me why that might occur? That includes you guys online. You've typed in only numbers so far. I want to see that you can type in words too. Come on, give it a shot. I know you know the answer. Right, because the prevalence is so low. The prevalence being so low means that there's many people in this population that don't have the disease. So even though the specificity is 90%, that's going to wind up meaning that we're going to get a lot of people that don't have the disease, 10% in fact, that don't have the disease. They're going to be misdiagnosed as being positive. So combination of the specificity, which even though it's 90%, right, and really mostly because of the low prevalence, winds up giving us a lot of false positives. And that's why we wind up with such a low positive predictive value in this case. Okay, let's get back to the exam. The next question basically asks you the same thing, doesn't it? Next question asks you what would be the best way, if you wanted to pick out one of these possibilities, what do you think would have the biggest impact on improving the positive predictive value? And I think most of you got the idea that applying the test to a population with a higher prevalence of disease is going to have the biggest impact. In other words, since its specificity is already 90%, increasing it to even 99% not going to have that big an impact. But if you apply it to a population where the prevalence is 30%, that's going to make a much bigger impact, right? And if the prevalence were lower, it would make the positive predictive value even a lower number. Okay, so I think most of you got the idea that we would be looking at 3. That's not to say that you couldn't improve the positive predictive value if it was slightly higher sensitivity, although it's already 99%, or that improving the specificity might not help as well. But I think it's pretty clear that the real driver here in terms of a poor positive predictive value is a low prevalence in the population. Okay, good. Let's move on to the next thing. Binomial distribution. Now, a few people stumbled on that, and it's really pretty simple. The hardest part about that is interpreting the word problem, number one, and then remembering how to apply the binomial distribution probabilities on Excel. So I'm going to go through these right now. In any given year, 1 in 3 Americans over the age of 65 will experience a fall. If you have 3 living grandparents over 65, assuming the probability for fall for each grandparent is independent, in other words, there's nothing that would suggest that like 2 grandparents are more likely to fall than maybe a third or something like that. Assuming they're independent, or that you did this on people over 65 that are that you selected randomly. Okay, so assuming that that's true, what's the probability that none of the grandparents will fall? Well, this is a binomial distribution, right? We have a sample size of 3, and we know the probability that of our success, in other words, somebody falling, is 1 in 3 or 33%. Right? So I'm going to open up Excel again, and I'm going to work with this binomial distribution. So our P, our probability, is 0.33. Probability of any individual in this population over 65 having a fall that year is 33%. The sample of our sample size is going to be 3. We're going to pick out 3 at random. In this case, it happens to be your grandparents. Okay, so now that we've picked them out, the probability is 0.33. Sample size is 3. And now we're going to look at what's defined as a success. In other words, somebody falling is defined as a success. And how many successes are we looking for here? Well, we're looking for 0 people falling that year, right? So none out of the 3 are going to fall. So let's apply the binomial distribution. Equals binom dist, parentheses, and immediately comes up as soon as I put the parentheses in, the open parentheses in, and prompts me the number of successes. Well, we're looking for the probability exactly 0 out of 3 trials, or sample size of 3, 0 out of 3, comma, are going to fall, and the probability of any particular person falling, the event occurring in any one of the random individuals, is 0.33, comma, and now cumulative, well, cumulative true would count 0 and everything below 0. So there's nothing below 0, right? So I could say false, which would just give me the probability for exactly 3, 0 out of 3, or I could say true, it should come out to the same thing. So I'm going to say true. I'm going to say true. And in fact, let me do this again. Equals binom dist, just to demonstrate that that's really true. True. Okay, is going to be 0, comma, 3, comma, 0.33, comma, false. And we get exactly the same result. So this is the probability for exactly 0 out of 3 grandparents having a fall during the period of that year. Okay, so let's move on to the next one. Okay, according to behavioral risk factors surveillance system, 58% of Americans have a sedentary lifestyle. Assuming that the surveillance system is correct, what is the probability of finding 8 or more individuals who are sedentary, in other words, one of those 58% of Americans, from a random sample of 10? So in this case, let's take a look at what our number of successes and our trials and so on and so forth are. So our probability that any individual in this population is sedentary is 0.58. Okay, our trial size or our sample size is we're going to pick 10 people out of this population, and we're interested in knowing the number of successes we're interested in finding out about is 8 or more. Okay, so let's apply this using our binomial distribution. Equals binom dist, parentheses. Now, number of successes. Well, since I know that I have an option here of putting in a number and either saying true or false, if I'm going to say it's true, it's going to give me the probability for that number of successes and all of the ones below it cumulatively. If I say false, it's only going to give it to me for that number of successes. Well, I don't want to say 8 because then 8 will be included, and we're looking for 8 or more. I know that since this works only going to the left or down, I know I have to put in 7 instead because I want the probability of 7 or fewer. Because once I know that probability, I know that 8 or more represents 1 minus that probability. So I'm going to put 7 in there. 7, comma, trial of 10, comma, 0.58 for the probability for any individual, comma, and then I'm going to say true because I want to know the cumulative probability for 7 out of 10, 6 out of 10, 5 out of 10, 4 out of 10, and so on and so forth. And that probability is 86%. So now the probability that 8 or more people are sedentary out of this group is equal to 1 minus the probability for 7 or fewer. Okay. The only unusual thing about that one that's harder than the one we did before is that in this particular case, we had to understand that we needed to find a probability for 7 or fewer in order to use this function to give us the probability for 8 or more. Okay, so you guys okay with that? Any questions about that? I know that was one of the problems that people struggled with a little bit. Let me know if that makes sense to you. Okay, all right, good. Okay, let's move on. Okay, using the file high school female athletes or either the Excel file or the high school file, the SPSS file, can be much easier with the SPSS file. Calculate the BMI for this sample. I'm going to look at the next few problems. Also, do them at the same time. Using the file high school females Excel or SAV, calculate standard deviation. Using the file again, calculate the interquartile range for this sample. Definitely it's looking like SPSS is a better tool for this because it's designed to do exactly this kind of stuff. Okay, and again, finally at the bottom here, it asks you to create a table, which, by the way, helps you do these various other problems and also produce a box plot, side-by-side box plot. So I'm going to go and open that up in SPSS. And I'm pretty sure I have this available to me now. Let's see where it is. It's in this one. Student athletes. Nope, student test scores. No, I don't see it there. Let me get it off Black. I'll go to Blackboard and pick it up there. Let me open a new window so I don't have to close that. And we go to the exam. Okay, I'm just going to save that SAV file to my desktop. So since that's really the one that I want to work with. And I'm going to open SPSS, which is going to bark at me because it expired and I'm on my 30-day grace period before I have to renew. Okay, don't need that. Okay, and I'm going to say open data. I'm going to navigate to the desktop. I already am. I'm going to click on that high school data, open, and that should read that data file for me. And indeed, there it is. Okay, so I'm interested in BMI. BMI is one of the variables here. Okay, in fact, I can see that I have many variables: name, sport, age, so on and so forth. I can click on the variable view, in which case each one of these columns, which represents a variable, a piece of data that's associated with each of the subjects, which are in the lines here in the horizontal lines, each one of those columns is going to be represented in the variable view. And one of them is going to be BMI. Here's BMI. BMI is a numeric variable. You can see SPSS has identified it as scalar as opposed to ordinal or nominal. Okay, so we know we're going to be able to work with it. It's a number. I'm going to go back to the data view. So I'm going to say analyze. I'm going to say descriptive statistics. And now I have a few choices. Frequency is usually reserved for nominal variables. It's just going to count rather than find averages and medians, means, and so on. Descriptives works with a variable. It doesn't allow you to split it up into different groups, but you can use it. So let's use that for starters. Okay, I'm going to move BMI into the box that identifies what variable that I want to work with. I'm going to click on options, and I can indeed get the mean, standard deviation. I can get the variance. I can get the range. I can so on and so forth. I'm going to continue. And let's see, I don't see a whole lot of things here in terms of getting more getting some graphics from this. So it's not going to provide that box plot for me. But I'll say OK anyway. SPSS then opens the output window, right? This is a separate window from the data window, from the data and variable view window. Okay, it opens it up, and it indeed has given me my mean, the average, arithmetic average or mean, the standard deviation, the variance, the range, and so on and so forth. Hasn't given me my interquartile range, the numbers that represent those values, right? And it hasn't provided me with a box plot. Now, I could go into graphs and ask it to create a box plot for me, but in fact, what I can do to shortcut that, to go to analyze descriptive statistics and go past descriptives to explore, which will give me some more options. Explore, and again, I'm going to move BMI, the variable I want to work with, into the dependence list. I'm not going to factor this up into different groups. If I wanted to compare one group's BMI to another group's BMI, I would move that categorical variable in here. Okay, if there were several categories, maybe by ethnicity, I could move ethnicity in here, and it would break it up into several groups where I could then observe what the average BMI was for each group and try and see if they're and trying to evaluate whether there's a difference or not. So I'm going to leave BMI there because I'm just looking at the overall BMI for all the student athletes. So I'm going to click on statistics. It's indeed going to do all these descriptive statistics for me. And in plots, well, let's see, it's already going to, you don't see box plot in here because by default, Explore always creates box plots for anything that you analyze. Okay, but I can ask it to do histograms as well. So I'm going to click off histograms. Perhaps I'd be interested in seeing how normally distributed these BMIs are for this sample. And then I'm going to click OK. Actually, before I do that, you might want to consider that if I just wanted the statistics, I'd click that. If I just wanted the box plot and the histogram, I'd click that. If I want both, I click both. I'm going to click OK. Again, SPSS opens the output window and adds these new statistical calculations to it. So let's see what we got. So here is the mean that we saw before, the median, the variance, and look, it gives us the interquartile range. That's something that was one of the questions that we didn't have before. And if I scroll up, I have a histogram for the distribution of BMIs. Right? Doesn't look all that normal, right? That looks a little skewed, but I'm going to go ahead and move on. And I have a histogram that represents the distribution of BMIs for this entire population as one. So the youngest person, the lowest BMI was 18. The highest BMI, the way I'm interpreting these feathers up here, is about 31. The median BMI was about 22, and they're student athletes after all. And the 25th percentile was about 21, and the 75th percentile was 26. So let's see, 21 to 26, that's a difference of 5. So our interquartile range is 5, as we observed before. Okay, so let's go back to this. So now, in addition to being asked to produce this box plot, you were also asked to upload it as a Word document. So in order to do that, or any other word processing program, in order to do that, you have to open up a Word document, and it asks for the table and for the graph. Okay, here's a blank document. Okay, so now I can go to my output window and I can click on the table that I'm interested in bringing over, click. And if you know, hang on a second, if I click into it, you'll notice now it's highlighted. If I click again, click away, it's not highlighted. Click, highlighted, click away, not highlighted. While it's highlighted, I can say copy or Control C, Command C or Control C, depending on what computer you're using. Okay, go in here to our Word document and say paste. Now, some of you, you're not going to see this on my computer because I have an issue with the installation on mine. I'm going to say paste. And here's the table. This table, because of the way I pasted it in here, is editable. I can go in here and highlight these numbers, change the color, change the font, so on and so forth. You can actually edit this table. If you wanted to, however, and the only problem with these tables is you'll notice that if I want to resize this table, well, this table is really, really a bunch of boxes, a real actual inserted table into Word. Okay, and it's a little bit cumbersome to just resize the thing or move it around the document. But in your case, if you go into edit, and instead of going into paste, you go into paste special, right? You'll see that you have the opportunity to tell it what format you want this chart pasted in here. Now you'll notice formatted text, that's the default. That's exactly what it did. You got the shading, you got the highlighting, you got the font that it was created in SPSS, but you also could insert it as unformatted text. You could also insert it as style text. I wouldn't worry about that too much. Now what's missing, this is my problem with this installation, what's missing here is inserting it as a JPEG or a .png file, as a picture. You should have the opportunity, if you say paste special, to choose insert as a picture here instead. And if you say okay to that and insert it as a picture, then if you click on this anywhere on the picture that represents this chart, then you'll be selecting the whole thing at once. You can easily move it around the document and resize it if you want to. So a lot of times, if you're not going to edit the chart, you just want to use it as is, that's a good option for you. You can just paste it in as you see it there. Or if you do want it, you want it as a picture, but you want to edit it to some degree, you can double click on it here, edit it here. Like if you don't need certain parts of it, remove those rows, for instance, and then copy and paste it in as a picture that you can move around the document much more easily. So just play around with that. I encourage you guys, use SPSS, use Word, use them together. Get as comfortable with them as you can. Because as you move on, they're going to be valuable to you in these other courses as you work on it. Okay, let me go back and finish this up now. Okay, so if you wanted to do this, you would then browse to your computer, upload the Word document that you saved, say, to your desktop, and you would be done with that problem. Okay, so question 16. Heights of 10-year-olds, regardless of gender, closely follow a normal distribution with a mean of 55 inches, standard deviation 6 inches. Use a distribution for the following. That distribution of 10-year-olds, mean 55, standard deviation is 6. What is the probability that a randomly chosen 10-year-old is shorter than 48 inches? Okay, well, how did we do that? I'll open it Excel again. How did we take care of that? Well, the mean of this population, mu, and the standard deviation, sigma, are 55 inches, and the standard deviation is equal to 6 inches. Okay, so when we're dealing with a population, if we want to know what percentage of that population is represented by a certain value, so for instance, shorter than 48 inches, right? What we're going to do is we're going to take that value, subtract the mean from it, and divide by the standard deviation. We really want to know what the number of standard deviation, number of sigmas that are different between those two values. Okay, and in this case, what does that represent? That represents something called the z-score. Z-score is basically just the number of standard deviations. So what's it going to be equal to? It's going to be equal to 48 minus 55 divided by 6. Whoops. Divided by 6. Okay, it comes out to minus 1.16 standard deviations. Now, if I go to my t-table, like my z-table, I'm getting ahead of myself here. Press the z-table. If I pull up my z-table, if I look at the z-table, it tells me my z-table tells me that for a z-score of negative 1.16, which I believe it was, humor me if it isn't, negative 1.16, negative 1.1, 0, 1, 2, 3, 4, 5, 6, negative 1.16 represents 12.3% of this area of the normal distribution, or percentage of people in that population, or you could also look at it as a probability that you would pick a person that's under 48 inches in this particular population. Okay, so if I go back here, 12 point, and just to show you the picture at the top of the chart demonstrates to you that the z-score that you've designated, these numbers in the center represent the area to the left of the z-score. Since it's a negative number, we know that that z-score is to the left of the mean. So this area is going to be less than 50%, right? Just as a little check that you can do mentally to make sure that you get it right. Okay, so let's look at the next problem. Next problem is, what's the probability of randomly chosen 10-year-old is between 60 and 65 inches. Okay, let's go back to our Excel. Whoops. Let me get that out of the way. See if I can't find Excel here. There we go. Between 60 and 65 inches. Okay, so we want to know the probability that they're between 60 and 65 inches. Okay, so now in this case, the mean is 55, standard deviation is 6, and I hope I didn't change the problem here, did I? 10 years, okay. Probability randomly chosen 10 years between 60 and 65. Okay, so in this case, the percentage of people that are under 65 inches tall, right? Well, how are we going to figure that out? Well, again, using this formula, it's going to be equal to x, the value we're interested in, 65 minus the mean, 55, divided by the standard deviation. So our z-score for 65 inches is 1.66. Well, what's our z-score for 60 inches? That's equal to 60, again, parentheses, 60 minus 55, x minus the mean, close parentheses, divided by the standard deviation, which is a z-score of 0.83, excuse me. So now, if I were to sketch these, right, what I would see is that both of these are to the right of the mean, because they're both bigger than the mean, 65 and 60, both bigger than the mean. So if I were to figure out what area is to the left of this z-score, I'm going to do it a different way this time. I could look it up on the z-table, right? But instead, I'm going to use Excel. Okay, so this is a z-score for 60. Well, the z-score for 65, okay, what area does that represent? Spread this out a little bit. The area that represents is norm, dist, parentheses, and if I put the z-score in here, it'll give me the area to the left of that z-score. I know, since it's a positive number, that it's bigger than 65, that the area to the left of that z-score is going to be bigger than 50%. Let's see what it comes out to. It comes out to be 95%. Now 60 is also to the left of the mean, right? But it's a smaller number. It's going to be more than 50%, but not as much as 65 inches tall. So it's going to be equal to norm S dis parentheses. Okay, and I'm going to tell it to look up the area for a z-score of 0.833, and that's equal to 79%. So what percentage of these girls are between 65 inches tall and 60 inches tall? Well, 95% of them are under 65, are under 65 inches tall. 79% of them are under 79 inches tall. 79% are under 60 inches tall. So if I subtract 79% from 95%, I'm going to be left with the percentage of people that are in between those two, or 15.4%. Okay, hopefully I got the right answer over there. Okay, running through this quickly. Okay, height requirement for this one is a little bit of a twist. The height requirement for Batman ride at Six Flags is 54 inches. What percentage of tests of 10-year-olds cannot go on this ride? Well, that's a twist here, isn't it? We want to know what if you have to be over 54 inches to go on this ride, what percentage of 10-year-olds are going to miss out? So we want to know what height represents the lowest 10% of the people in this population. Well, let's see how I'm going to do that. If I know that I'm looking for an area to the left of 10%, in other words, the shortest 10% of people are going to be in here, I want to know what the z-score that represents that 10% is. It's the problem is asking me the height requirement is 54 inches, right? Okay. What percent? I'm sorry. What percent? What percentage of 10-year-olds? Oh, I'm sorry. You're right. What percentage of 10-year-olds? You want to know what percentage of 10-year-olds are under 54 inches? Excuse me. I was thinking of another problem. I was thinking of a problem I should have asked there. Okay, you're absolutely right. So we want to know what percentage of children in this group are less than 54 inches tall. Okay, so basically same problem as we did before, except this time we're looking at 54 inches. 54 inches. So let's figure out what the z-score for that is. It's equal to 54 minus 55, close parentheses, divided by 6. So the z-score is going to be equal to negative 0.166, and the area that represents is going to be, it's a negative number, so it's going to be less than 50%. Parentheses. Okay, it's going to be, that's z, and it's going to be equal to 43% of the girls of these children are under that height. I hope I answered the right question there. And while we're at it, I want to ask you the question that I didn't ask. 0.43? I'll take a look at it. Okay. Let's see. Let me just make sure I'm answering the right question. High requirements, 54. What percentage of 10-year-olds cannot go on this ride? Yeah, okay. That should be right. Okay. So let me ask you the question I meant to ask. What is the height that if I were to say I am going to eliminate the lowest 10% of these children from taking this ride, the lowest 10% in height are not going to be able to take this ride. What height does that represent? In other words, what number represents the lowest 10% or 10 percentile? In other words, if you took an exam, the lowest 10% of the scores, for instance. Well, that's 10% of the area of this distribution is a 10th percentile, right? So if I wanted to know what that number is, I really don't know what the number is yet, but I certainly can find out what z-score represents, an area of 10% on the left part of this normal distribution. And I can do that by using this table backwards. I can look at this table and say, let's look for 10%. And the area representing 10%, the closest thing to 10%, looks like it is right here, right? Which is negative 1.28. Negative 1.28 is the z-score that represents that area. Okay, let me get Excel back. Negative 1.28. The z-score that represents 10%, the lowest 10%, is negative 1.28. Okay, that's the z-score. Okay, so now I want to know, well, what height does that represent, that negative 1.28? Well, you may remember that we were able to, we used a formula that z is equal to the value we're interested in minus the mean, right, divided by the standard deviation, sigma, right? So I'm going to put this in parentheses here so there's no confusion. Okay, in this case, I know what z is. I know that z is equal to negative 1.28. Okay, I know that mu, negative 1.28. I know that mu is equal to, what was it, 55? Is equal to 55. And I know that sigma is equal to 6. The only thing I don't know in this formula is what x is, right? So I actually can solve for x here. So if I can multiply both sides by sigma, it cancels out here. So the left side of this equation becomes equal to z times sigma. And the right side of this equation becomes x minus mu. X, what did we say? Let's see, what did we say that mu was? X minus mu, x minus 55. So all I have to do is move that 55 over to the other side. Okay, so that's going to be equal to 55 minus, that's a positive number, 55, minus 7.68. So x, oops, I messed up there, equals 55 plus a minus 7.68 equals 55 plus a minus 7.68, okay, which is 47 inches. So x is 47.3 inches. That's the height that represents anything below that is in the lowest 10% of this distribution. Okay, maybe a little easier to see if I drew it out as a graph, but that's what we wind up with now. Okay, so let's look at the Venn diagrams now, and then finish this up. Okay, best configuration, the best description for this Venn diagram. Okay, well, we see that this represents B, right? So actually, let's see, A, no, don't look like that's a possibility. A union B would represent either one. You look at it in terms of it could be A or B or both, and that's not the case here. A intersection B would have to satisfy both A and B, and only this part does that. So basically, it's just going to be B. We know that. How about this one? Well, I just gave that one away, right? It could be either A or B or both, which is basically A union B. And what about this one? Let's see. Well, this one represents A, but it doesn't represent it doesn't represent B. So in other words, it is A, but it's A and the intersection of not B. In other words, it's got to satisfy both conditions. Does it satisfy A? No, it doesn't, because it leaves part of it out. Does it satisfy B? Not at all. Does it satisfy A union B, which means it can be either A or B or both? No, that's not the case. So the only thing left is A intersection B. Does it satisfy both those conditions? Well, yes, it satisfies the condition A, but at the same time, not being B, excluding the part that contains B, right? So we know that it's that one. Okay, you could have done it just by elimination or by reasoning out what that stands for. Okay, this is a longer test than I anticipated. The heights of male soccer players are normally distributed with a mean of 69 inches and a standard deviation of 3 inches. Now, it's good that we're going to talk about this because this is where we're going with this stuff. Okay, given the empirical formula, what is the probability of randomly selecting a player between 66 and 72 inches? Well, 69 inches, 3 inches under the mean, 3 inches above the mean. So we know that represents about 68% of the possibility, right? 68% probability. The heights of male soccer players randomly distributed with a mean of 69 inches, standard deviation 3 inches, using comparing for what's the probability of randomly selected player being less than 63 inches tall. Well, that is 2 standard deviations below the mean of 69. So we know that 2 standard deviations above to 2 standard deviations above represents about 95%, which leaves a tail of 2.5% at each end. So what percentage is going to be smaller than that? Well, it's going to be 0.25, 2.5%. The heights of male soccer players are normally distributed 90, 69 inches, standard deviation of 3, using Excel statistical function or Z-table. What's the probability of randomly selecting a player that is more than 73 inches tall? Okay, well, let's see, more than 73 inches tall. So let's get into this. Okay, so mu is 69. The standard deviation sigma is 3. And we're interested in an x that's equal to 72 inches. Okay, so what's the probability of this coming up? Let's see, what's going to be equal to, I could use Excel to calculate the z-score, right? What's the z-score equal to? It's going to be equal to 73. Okay, let's go back and take a look. 73, you're right. Okay, 73. Okay, so let's calculate our z-score. Z, right? Our z-score is going to be equal to. It's going to be equal to x minus mu, close parentheses, divided by sigma, number of standard deviations. It's a positive number because 73 is to the right of 69. That's equal to 1.33. What probability were we looking for again? Probability that someone's greater than 73 inches tall. Well, this only works to the left. So we first got to find out probability of being less than 73 inches tall. And we can use norm S dist, parentheses, and the probability is going to be equal to, let's see, norm S dist, the z-score is 1.33. So that area, which we know is going to come out to be more than 50%, is equal to almost 91%. And to find the probability somebody's going to be greater than 73, it's going to be equal to 1 minus 90%. In other words, what's left above the height of 73. So it's going to be about 9%. Okay, great. So now let me show you a little trick here. There's another function here that's called Normdist. When I hit parentheses, it'll tell you what it needs to do to complete this function. Parentheses. Well, look, it needs x, the mean, the standard deviation, and cumulative. Okay, let's give it what it needs. X was 73 inches, if I recall correctly. The mean is 69%, comma, and the standard deviation is equal to 3, comma. Cumulative is always referring to an area, so it's always going to be true for cumulative with this function. You're never going to use false with this function. Let's see what I wind up getting. I wind up getting my 90%. It automatically gives you the percentages bypassing the need to figure out what the z-score is. And from there you can say that the area you're looking for, which is above, is equal to 1 minus that. So you can play around with these functions a little bit. Okay, so I hope a couple of you are still awake out there. And we're almost at the end of this. The heights of the male soccer players, okay, that's that one. The heights of male soccer players are normally distributed to mean of 69 inches, so on and so forth. This sigma is 3. If you take repeated samples of size 36, hence our segue into what we're working on next. If you take repeated samples of size 36, you would expect the means of these samples to produce a new distribution with a mean that approximates the population mean, 69. Makes sense, right? If you repeatedly take samples of size 36, sometimes you'll get 68, sometimes 72, sometimes 70, but the average of all of those sample means is going to approximate the population mean. However, the variability in sample is going to be smaller. In other words, the mean, when you take 36 people and you average them, the distance from the mean for that mean of that sample is going to be less than the variability of the actual individuals in that population. How much less is it going to be? It's going to be sigma, the standard deviation of population, divided by the square root of the sample size. So what's that going to be? What would you expect the standard deviation to be for 36? Well, it's going to be the standard deviation, which is 3, divided by the square root of the sample size, 36. Square root of 36 is 6. So 3 over 6 is 0.5. So that's going to be your standard deviation. So that's